Hi, students. This PowerPoint is on chapter 11, and it's on sections 2 and 3. If you're following along in the packet, we are starting on page 125. Okay. So this whole chapter is about solutions. I already talked about this in the last video. So that solutions are homogeneous mixtures of two or more substances, and the solute is dispersed throughout the solvent. This was mentioned already, okay? The thing that we want to talk about a lot in this video is that solutes and solvents interact through intermolecular forces. And so this is going to continue with our intermolecular force talk that we had before. But on the bottom there is just showing you that solutions can come in lots of forms. They aren't all liquids. We're used to liquid solutions, but we can have solutions where we have the state of the solution is the gas or the solid. So it's just showing you there's lots of different types of solutions. Okay, so here's some of the intermolecular forces that you're going to see in solutions. The main ones are going to be ion dipole, hydrogen bonding, dipole, and London dispersion. The numbers here, where you see these numbers here, okay, those are telling us the bond energies. So it's telling us how much energy it would take to break that force. And as you can see, ion dipole is a big range, but it's the strongest. Then hydrogen bonding, then dipole, and then London dispersion. There's a lot of overlap. You could have London dispersion that's stronger than dipole, but most of it on average is weaker. And the difference between this and it's not really different. There's no difference between the intermolecular forces we talked about before. It's that in a solution, instead of having water that is intermolecularly bonded to other waters, it's going to be to the solute. So if this is the we've got solvent and solute. We have a solvent intermolecular force to a solute. So there are two different molecules in that. So we're going to talk about a few different factors that affect solubility. Solubility is, in general, the word solubility means the amount of solute that will dissolve in a given amount of solvent. So it's a number, but in some things, sometimes we just say it is soluble or it isn't soluble. And what that means is we're kind of drawing a line in the sand. We're saying, well, if the solubility is higher than a certain amount, usually about 0.01 or 0.1 in their moles per liter, then we call it we say it's soluble. We say that solute is soluble in that solvent. So we like to use this axiom. It's very generalized, but it says like dissolves like. And so it's more of a tendency. It's not a rule. So it tells us that polar and ionic substances will tend to dissolve in polar solvents, and nonpolar substances will tend to dissolve in nonpolar solvents. It's not 100% true all the time. There are ionic substances that do not dissolve in, let's say, water, and there's some that do. But it's just sort of the tendency which way it's going to go, okay? And it doesn't mean some nonpolar substances will dissolve in a polar solvent. It's just not as high a degree, so it's a matter of degree. So this is explaining part of the reason why. The stronger the intermolecular attraction between the solute and the solvent, the more likely the solute will dissolve. And so the example here is ethanol in water. And it's showing here, here's an ethanol molecule here, and here's the water. And because they have a hydrogen bond between them, they will tend to mix very well with each other. Here is one ethanol molecule and another ethanol molecule. My pointer out. So here's two ethanol molecules, and they can form a hydrogen bond. This little blue thing here is the hydrogen bond. So they have a hydrogen bond, and so they form a liquid with each other. But this is showing that, well, water will also do that. So they're going to tend to mix really well as they have similar intermolecular forces. So the hydrogen bonding is the main one. Of course, everything has London dispersion, so that's another one that we have here's just showing you how that can go here. So over here on the right, this is a glucose molecule. And this part here, this up and down ring here, there's an oxygen right here, but every place else that there's a point, just like we learned in a while ago when we were looking at these kind of molecules, these are carbons. And so it's glucose here, it says is C6H12O6. So these are a bunch of carbons, carbon, 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 and then one here. And you see that glucose, glucose is a sugar. If you have blood, when you talk about blood sugar, that's the sugar of glucose. Regular table sugar or sugar that you have in a candy bar or something is sucrose. And sucrose is half glucose and half fructose. The molecules are bonded together. So glucose is in a lot of the foods we eat. Starch, when you eat something that's starchy, very carby, starchy food like breads and pastas and rices have starch in them, and that starch, when it breaks down into glucose. So here's glucose, and this guy is cyclohexane, C6H12. So it's similar in size. It's a little bit lighter, not quite as heavy, doesn't have as many oxygens as the glucose, but it's about the same shape. It's this ring here. See how it is up and down of the carbons in the ring? So that's about the same. But if you compare these two, glucose is very soluble in water and cyclohexane is not. So, and that's because glucose has these hydrogen bonds. So when we say it has hydrogen bonding, it can hydrogen bond with the water molecules. So basically water will be attracted to the glucose. It's not that water is not attracted to cyclohexane. It would be attracted to it by London dispersion. All molecules attract each other, but it wouldn't be very attracted to it. And so the thing is that in order for water to bond to hydrogen bond to glucose, it has to not hydrogen bond with itself as much. So think about a water molecule coming right in here, okay, on this OH. In order for it to form a hydrogen bond here, it would have to break a hydrogen bond with with another water molecule. So if it breaks one hydrogen bond, but then it forms another, that's not a big difference in energy because you're breaking a hydrogen bond and you're forming another. So breaking intermolecular forces takes energy, but forming intermolecular forces releases energy. So if the bond you break between the water and the other water is about the same energy as the bond to this, then it doesn't take as much energy to do. Here, in order for water to have London dispersion forces, like to surround this cyclohexane and have London dispersion forces with it, it would have to break bonds to other waters to do that. And that's just not energetically favorable. So that's what happens with solubility. It needs that like dissolves like. So here's a couple of vitamins. Here's vitamin A, lots of carbons here, and then one OH group down here. So there could be hydrogen bonding going on here, but the rest of this, if water was going to surround this, water would have to surround the whole thing. And over here, it would only have London dispersion forces on this non-polar side here. Over here, here's vitamin C, and vitamin C has lots more places where it can form hydrogen bonds to water. Even these oxygens here have lone pairs, so they could hydrogen bond to water. And so vitamin A is soluble in non-polar substances like fats and oils. And then vitamin C is very soluble in water. And so you can see the difference here with the hydrogen bonding capability. So here's another example. Here's vitamin B6, here's vitamin E. Vitamin B6, and in these pictures here, these red atoms are the oxygens. This blue one is a nitrogen. So over here we have an oxygen bonded to a hydrogen. The black atoms are carbons, the white ones are the hydrogens. So this is an OH group, here's this one, here's an OH group, here's another OH group. And then this is the nitrogen, and this nitrogen has no hydrogens, but it does have a lone pair, actually 2 lone pairs on it. So it would have possibility of hydrogen bonding in like different parts of the molecule. So here's vitamin E. This whole long carbon hydrogen part here, this tail going on here, that does not have any hydrogen bonding capabilities with water. It's very non-polar. This part of it's very non-polar. there's an oxygen here, an OH group here, but overall, if you look at the whole molecule, it's very hard for water to have strong intermolecular forces with it. So which vitamin is water and which is fat soluble? Well, I hope you would say that this is water and this is fat soluble. If you've ever seen a vitamin E tablet, they tend to come in oil. So if you've ever seen, I said if you've ever seen a vitamin E tablet, you would be seeing it probably in an oil form. At the end of the video, I'll show you one. Okay, so this is related to all this, in that this is how soap works. So this over here, this molecule here is a soap molecule. And I posted a video on YouTube that shows you in a little bit more detail about where the soap comes from. It comes from fats that have been chemically chopped up, kind of. So you'll see that in the video. But this is the soap molecule. Detergent molecules and soap molecules are really very, very similar. It just has to do with where their source comes from. But you can look it up if you're interested. But here, these molecules here, see this long part here? These are carbons and hydrogens. So in this depiction, the carbons are the black atoms and the hydrogens are blue. So this is this long non-polar tail, we call it. But on this end of the soap, we have carbon, and these are two oxygens, and it's not just polar, it's charged. It's actually an ion. And then there's a sodium ion over here. So this guy is called sodium stearate. So here's the sodium, and this is the stearate ion. 18 carbons, 35 hydrogens, and the C and 2 O's. So it's really a mixed bag here. It's got a non-polar part, and as we know, non-polar only it has London dispersion as its only intermolecular force. So if this is going to bond to another molecule, it's going to have London dispersions here. But this then is an ion. So not only it's not even just polar, but it would have like ion dipole forces if it was bonding, let's say, to water as an intermolecular force. The sodium is just a spectator all this. So this is how soap works. So what's happening here is this part here, the background here is water. Okay, they're showing a few, they're not even showing the water molecules, okay? But this is all in water. And what happens is this part down here in gray, this gray stuff is supposed to be like an oily grease stain. So imagine if you've ever worked with oil or grease, either because you're working on a car or a bike, or maybe you're cooking and you get oil on your hands. If you just put your hands under some water, then nothing's going to really happen. The water just kind of washes away. Because if we say, oil and water don't mix, right? Well, oil and water don't mix because their intermolecular forces don't go together. The oil is nonpolar and the water is polar and can hydrogen bond. So they're not going to mix because their intermolecular forces aren't right for each other. And so down here, then this gray part is supposed to be a big clump of oily molecules. So, and the oily molecules have lots of carbon and hydrogens in them, very nonpolar. So what happens is the soap comes, and this part of the soap, the tail here, that can insert itself in this grease here. And it forms, in the video you'll see on YouTube, the little animation, it forms what's called a micelle. And what happens is this negative over here, this guy here, is on the outside. And it's showing here, this is all water. It's showing a few water molecules bonded to it. See these little dotted lines here? The dotted lines are the hydrogen bonds. These guys are little water molecules, water, 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 water. So the water gets attracted. So you probably heard the terms, if you've taken biology, I'm sure you've heard it. This part here is what we call hydrophobic, this end of the soap. It does not hydrogen bond to water, so it's hydrophobic. That means water fearing. It's not really fearing the water, it just doesn't have much interaction with it because water won't have intermolecular forces with it. This side here, because it's negatively charged, is hydrophilic, meaning water loving, or water will bond to it. So these are ion dipole forces, these guys here. If I said hydrogen bonds, I'm sorry, I was trying to out here, these little dotted lines. Those are going to be some hydrogen bonds, but mostly ion dipole forces. And then down in here, we have the London dispersion going on inside. So what you end up happening is this outside of this now greasy thing is now charged, and it can be washed away because the water will interact with it. So go ahead and watch that video to show. I also posted another video that's really interesting that shows how soap kills the coronavirus. Not all viruses are broken apart by soap, but the coronavirus has some lipids, which are fat molecules inside its membrane. And so there's a cool video animation I posted that shows you how that works. Okay, so another topic here that has to do with how things dissolve and why things dissolve and factors that affect it are going to have to do with gases. So if we look at a gas, gases will dissolve in water. So the arrow on the carbon monoxide, ignore that for a moment. Look at the other ones. We have nitrogen, oxygen, argon, and krypton. And this says, in general, the solubility of gases in water increases with mass. If you look at the molar masses here, nitrogen is the lightest, and then oxygen, then argon, then krypton. And I'm saying, don't worry about the carbon monoxide yet. And you notice they're not very soluble. The solubility here, this is in moles per liter. So how many moles of this gas will dissolve per liter of solution? And you can see nitrogen is about 0.7 times 10 to the minus 3. Oxygen's about double that. Argon's higher, and then krypton's, about 2.8. So these are all non-polar substances. So they don't dissolve very much in the water because water is polar and it does hydrogen bonding, and these would only have dispersion forces with the water. So it doesn't have a high solubility, 10 to the minus 3 order. But you see it does go up as we go heavier and heavier because the larger molecules will allow for stronger dispersion forces. So they're non-polar, they don't dissolve very much in the water, but the bigger they are, the more dispersion there can be, and then they dissolve better. Carbon monoxide is a polar molecule because the oxygen has a higher electronegativity than the carbon. It has but it does like to be in the gas phase, so it's still hard to dissolve in the water, not a very high solubility here. It has about the same molar mass as nitrogen. And you notice it has a higher solubility, not quite double, but a higher solubility. And that's because it is polar. So it has more than just dispersion with water. It can do the dipole. So another thing that can affect the solubility of gases in solution is pressure. And so this is showing down here that we've got some water and we've got these purple or lilac molecules in here. And some of them are in the liquid, they're dissolved, and then some of them are going into the gas phase. So this is not like when we were looking at vapor pressure, where the molecules were the same molecules here. This we have now as solute dissolved in the water as opposed to just water. This is not really vapor pressure. This is the pressure of there is vapor pressure because the liquid can go into the gas phase, but we're not just talking about the vapor pressure here. We're talking about, well, the gas is going to dissolve in the water, but then some of it's going to come out, okay? And then some of it's going to go back in. So this is a gas like oxygen dissolved in water. And this is increasing the pressure above the solution forces more gas to dissolve. And what happens is, so as you push down, as you increase the pressure on it, more is going to dissolve. Liquids and solids don't really have their solubility change much with pressure, but gases do. It is directly proportional to the pressure above it. And so that's related by something called Henry's law, which is right here. You're not going to have to do any calculations with Henry's law. So there are some in the back of the chapter that I didn't assign any to calculate though. So, but just so you see what's going on here, Sg, this is the solubility of the gas in the liquid. K is the Henry's law constant. So it's not always the same number. Henry's law there's more than one Henry's law constant. Every gas and every solvent pair has their own Henry's law constant. And P is the partial pressure of the gas above the liquid. So as the pressure goes up, the solubility goes up because K is a constant for that pair. And as the pressure goes down, the solubility goes down because K for that pair is a constant. So over here, we got a picture of carbon dioxide dissolved in water, which is what you have in typical sodas. And what happens is you can see that they've opened this here a little bit, so the the pressure is being released. If you imagine what this looked like before, you wouldn't see all these bubbles, right? And you've all you open those a bottle here and of carbonated beverage, and you hear that come out. Well, that's because when these are bottled, they have a higher pressure. They pressurize them when they bottle them. And that allows the carbon dioxide to be more soluble. So because the pressure is higher when it's bottled, the solubility is higher and it stays in. Then when you open it, you release that pressure that they've got in there. And now the pressure above it equalizes with the atmospheric pressure. So now the pressure has gone down, so the solubility of the gas goes down, and that's why it starts, you see the bubbles forming. The bubbles are the gas coming out of solution. When the gas is dissolved in solution, just like anything else dissolves, you can't see it. So the bubbles you see are from the gas coming out of solution. All right, so temperature depends on how it affects solubility. Most solids will have a higher solubility if you increase the temperature. But there are exceptions, not all of them, but most of them will. These are a bunch of ionic solids, and we're showing how their solubility increases with changes with temperature, mostly increase, although this guy is going down. In lab, if you're doing experiment 13, you're studying this one, potassium nitrate. And so you're saying what happens to its solubility as a function of temperature. It's not quite linear, although over the range you're studying in lab, it's about this part, so it's pretty linear. And you notice it's very different for all these, but most of them increase with temperature. What I always find interesting about this is all of these, maybe not this one, but all of these, yeah, all of these would be, if you looked on a solubility table, we would say these are soluble. So all of these are soluble, but look how differently they behave. Even if you go for room temperature, which is around 25 degrees, look at how different. So if I go, here's 25 degrees. If I go up and read across, that tells me how soluble it is. So let's just go straight up here to this line here, sodium chloride. So it's got a solubility of about 35 grams in 100 grams of water. That means if I had 100 grams of water, I could put 35 grams of sodium chloride in it and it would still dissolve, it would keep dissolving. If I put 36, that last 1 gram wouldn't dissolve. If I keep going up though, look at like lead nitrate. It has a much higher solubility. Sodium nitrate, like 95 or so, or 94 grams of it dissolves in 100 grams of water at that temperature. So they're all soluble, but they have different amounts of solubility and they have different temperature effects. Sodium chloride from 0 degrees to about 100 degrees, almost the same solubility, but some of these have much higher effects with temperature. So what do you have to know? Well, you just have to know that in general, the solids do have a higher solubility with temperature. Most of them do. You don't have to know this chart. It'd be good to be able to read it, but you don't have to memorize it or anything. Now, the opposite is true of gases. Higher temperature drives gases out of solution. And so therefore, if you have a carbonated soft drink, they stay more bubbly if you store it in the refrigerator. If you put it out, it's going, we could say it goes flat. It goes flat faster at warmer temperatures. Now, of course, that's if it's opened, okay? If it's not opened yet, if you haven't like broke the seal, it will be fine either way. Warm lakes have less oxygen dissolved in them than cool lakes, and that could affect, the aquatic life in there. And you see that this here is a graph of the solubility of the gas in water as a function of temperature. The units here are different than the last one. This is in millimolar, so millimoles per liter that will dissolve. And you see oxygen here at cold temperatures, we have a high concentration, but as you warm it, the concentration goes down quite a bit. Okay, so a few definitions left, and then we're done with sort of the definition part here. Degrees of saturation. So you could have a saturated solution, and that's when you have as much solute that you can have in there at that temperature. If you put any more in, it will just sit down here at the bottom without dissolving. So that means it's saturated. You might see some undissolved solid in the flask. That's how you know for sure it's saturated. And it's an equilibrium. So what's happening is It's not always the same particles that are in the solid that are in the solution. It's like something a little bit dissolves and another little bit comes back, but you still have the maximum amount of solute that can be dissolved. The water can't, or whatever the solvent can't hold anymore. Unsaturated solution, excuse me, means that you're not at that level yet. You have less than the maximum amount. Most of the solutions we work with in lab are unsaturated, right? You don't have any solids sitting at the bottom. That means that you could put more in if you needed to. And it says no solid remains in flux. This is not just for a solid liquid solution. Those are the most common ones, but so it could be no, it should say no remaining solute is really more general way to say it. Now you also have this interesting case called supersaturation, and that when you have, actually there's more solute than is normally possible at that temperature. And the way that that happens is this right here is our supersaturated solution. You can't tell by looking at it. It looks just like it's unsaturated. What they've done is they've put in more solute than should be able to be dissolved. They have extra solute in there. So they started with stuff where there's a lot of solid in the bottom, okay? And then they heated it up to a higher temperature, and then it dissolves. And then you let it cool really slowly and don't touch it. Don't stir it, don't touch it. So there really is more in their solid that should be dissolved than there should be. But because you're being very still and it's not moving, that the crystallization process hasn't started yet. So crystals need a place to grow. They need sometimes a seed crystal or some movement to help them go in. But if you're very careful, it can just sit there and be unsaturated. They're very unstable, okay? And so what this is showing is like this is a little seed crystal they're putting in here, and then suddenly it crystallizes. I have a very short video of this with, I believe it's sodium acetate, which is kind of cool to watch. You can take a look at that. Okay. So now we're going to talk about energy a bit. And this is the last topic in this PowerPoint. And this is going to the heart of, well, why do some solutes dissolve in some solvents and others don't? And I was hinting about that before because we were talking about the intermolecular forces and how they have to be the right amount of intermolecular force. This is going to go into a little bit more detail of that. So and we're going to focus on solids dissolving in liquids because it's the easiest thing to picture, but this actually goes for gases in liquids, liquids in liquids, a gas in another gas. It doesn't matter, it goes for any solution, but it's just kind of easier to picture with the solid and the liquid. And in fact, we're going to kind of focus on an ionic solid in liquid, so salt water, because it's the easiest to picture. So what drives the dissolution process? Dissolution is the solution, forming of the solution, the dissolving process. What drives that process? Why is it happening? And this is the answer, the energetics of the dissolving. So in a couple of definitions, and then we'll get to it. All right, so how does it happen? Well, we've talked about this back in chapter 4. The solvent molecules are attracted to the surface ions. Well, we now know that that's, in this ionic solid, that's gonna be a ion dipole force. So before we would just say they're attracted, now we know it's called an ion dipole force. Each ion is surrounded by the solvent. So you see that happening here. See all these ion dipole forces happening here as it's dissolved. And then there's enthalpy changes anytime you have an interaction that's broken or formed. So if you have an interaction that's broken, in other words, here, this is an ionic bond that's being broken here. It takes energy to do that. If a bond is formed, or it doesn't matter whether, so we call things bonds and then intermolecular forces, right? So we call things covalent bonds, ionic bonds, and then we have intermolecular forces. Nature doesn't know that we did that we called them different things. Nature just knows that some things stick together, okay? And then sometimes when things are stuck together, we break them apart. If they're stuck together and we break them apart, we got to put energy in to do that. It doesn't matter whether we're breaking a covalent bond or an ionic bond or a hydrogen bond or a London dispersion force. If they're stuck to each other and we separate them, we have to put energy in. The opposite is also true. It doesn't matter how they're coming together, but if two particles come together, a positive and negative ion forms an ionic bond. Two atoms form a covalent bond. Two molecules form a dipole-dipole interaction. Whatever it is that's making them stick together doesn't matter, but when that happens, energy is released. So energy is when you break an interaction, you have to put energy in, and when an interaction forms, energy is released. So that's what number 3 is about, the enthalpy change, which is the heat energy change with each interaction broken or formed. That's what we're going to look at. Okay, a couple of definitions. We're focusing on ionics right now because we kind of know a lot about them, so they're easier to look at. When an ion is solvated, it means surrounded by solvent. If the solvent is water, we call it being hydrated. Okay, so these are all, these blue sticks here are just representative of our ion dipole interaction. So we have an ion and water is a polar molecule. So this is an ion dipole. So you see this sodium here, it has 1, 2, 3, 4, 5, 6 waters around it. And the chlorine has 1, 2, 3, 4, looks like 5 around it. Could have 6. You know, this one, they do different things. So this one has 2 over here. This could 1 over here. Could have 2. But anyway, they're surrounded by water. It's hydrated. Okay, and the intermolecular force here is ion dipole. Okay, so this is the detail of how this happens. Now, this is not a step-by-step of what actually happens. The atoms and the molecules don't do this little dance here. Everything kind of happens at once. But the beauty of studying energy steps is that you can look at the steps as if they were happening one at a time, and you get the same result, okay? So we're gonna look at it as if the process happened in 3 steps, but they're really kind of all happening at once. So the first one is that the solute particles at some point have to separate. So you see over here, this is our salt, right? In order for them to get dissolved, they have to be separated from each other. There's ionic bonds here, and they're gonna have to be broken. Because when we get to the solution, which down here, see the final solution down here, there's no more bond. Well, maybe there's one still stuck together. We'll get to that later, but mostly they're all separated from each other in the solution. So all those ionic bonds, or most of them, have to be broken. That takes energy. The amount of energy that takes to separate the solute, they're saying molecules, ions, particles really, from each other, we're gonna call delta H1 endothermic step. Okay, now this is, let's say, the water, and before you put the salt in, they're all got hydrogen bonds with each other or whatever if it's a different solvent. In order for them to be able to bond with the particles of solute, some of those, not all, but some of those intermolecular forces of the solvent have to be broken. So separation of solvent particles to make holes. Now they're not actually making holes, okay? But what we're saying is that in order for this to happen down here, we have to break some of these intermolecular forces. Not all of them. See, like down here, there's still here. But there's got to be a way for that solute to be in there. So that's also an endo step. We're going to break some hydrogen bonds, and that's delta H2. Now what happens is, though, the solute and the solvent now make their new intermolecular force. If it's ions and dipoles, then it's ion dipole. And when that happens, see these little forces, interactions here, now you've formed a new intermolecular force, and that's an exothermic step with like 2 breakings and 1 forming. 2 interactions broken, 1 form. Now it's not just two types of interactions in 1 new type forming. Okay, looks kind of complicated. Not that complicated. There's 2 cases here. Let's look at the one on the left. Here's our starting point before anything happens. This is the energy that we have to put in to separate the solute particles from each other. That's our delta H1. That's an endothermic step. So enthalpy going up, adding energy. We have to put more energy in, and we have to separate those solvent particles from each other. If it's water, we're breaking some hydrogen bonds between water molecules. Then when those solute and solvent make their, for example, ion dipole forces, boom, energy is released. This guy here is the net change in energy, because if you're putting this much energy in and this much comes out, then this is the net change. And in this case, it's a negative, it's downward change, and that would make it an exothermic process. We call this overall change the heat or the enthalpy of solution, how much energy it is released, for example, when a solution is made. In this case on the left, it's an exothermic process, and what would happen is as you mix them together and they form the solution, it would get warm. You saw this in lab. Well, probably, maybe we didn't do the lab before we left to go online, but if you were to do the lab in person, when you put, if you mix certain things together, like sodium hydroxide and water, it gets warm. And when it gets warm, it's because of this, because it's an exothermic solution forming. And it's because the delta H1 and the delta H2 added together are less than the delta H3 that's released. Not all solutions are exothermic forming. Some of them are endothermic. In that case, the energy to break the particles from each other, the original bonds. So this delta H1 and delta H2 is like the original bonds holding the particles together. The amount of that energy it takes to break is more than what's released when the solution forms. So in this, we have a delta H of solution that's positive, which is endothermic. So there's both possible, and it depends on the values of these H1, H2, and delta H3. Okay, so the delta H of solution comes from delta H1 plus delta H2 plus delta H3, okay? And as we mentioned before, they can be either positive or negative. Here's an example. If we dissolve magnesium sulfate in water, it releases a lot of energy. It's pretty exothermic. So if you ever have magnesium sulfate is Epsom salt. So if you ever put that into water, you'll feel that it gets very warm on doing that. Ammonium nitrate is pretty endothermic. That's used in things like cold packs, like when you have those instant cold packs where you kind of crush it up and it gets cold. So basically if you take this salt, ammonium nitrate, and put it into water, it's going to get really cold because it's an endothermic. So what's happening here is in the exothermic, it's kind of easy to understand. It's releasing energy to the surroundings. In the endothermic one, in order for this ammonium nitrate to dissolve, it actually has to take energy from the surroundings in order to do that. So that's why it feels cold. Okay, so a couple of definitions that's going to help you with a couple of the homework problems. In ionic compounds, there's something called the lattice energy, and the lattice energy has to do with how much energy it takes to either form a salt or break up a salt, but not in water, just like the ionic bonds themselves. So the thing to keep in mind is that delta H1, that step where you break apart the solute particles from each other, for an ionic compound, delta H1 is equal to the negative of its lattice energy. And that's something you can look up or can be given to you. There's another term that's called the enthalpy of hydration. And that's the process occurring in steps 2 and 3. And that's when the particles are already separated into the ions, and now they're going to be hydrated with the water. So step 2 and 3 added together gives us something called the enthalpy of hydration. So the heat of the solution, which is 1 plus 2 plus 3, can be found by taking the negative of the lattice energy, which is 1, and the enthalpy of hydration, which is 2 and 3. So if you have these numbers, if someone tells you these numbers, you can find the heat of solution. And there's a homework problem or two where they give you those. Okay, so this kind of says what's going on here in that why certain things dissolve in certain solvents and others don't. What is solubility all about? All right. The degree of solubility of a compound depends on a large part on that delta H of solution. Energy is what's driving this. So if your delta H solution is positive and endothermic, it's taking energy in from the surroundings in order for the substance to be dissolved. So if the solution is cold when you make the solution, it's taking energy in from the surroundings to do that. But what if there's not enough energy in the surroundings? It won't work. Sometimes you have to warm it up to get it to happen. And otherwise it might not happen in cold temperatures or in room temperatures. Sometimes it doesn't happen no matter how much you heat it. So, or it would have to heat it quite high in order to do it. So just the general thing. I'm not going to ask you to memorize or come up with this. There is a homework problem where it asks you to discuss it a little bit. It's more of a thought thing. So if you have a polar solute and a polar solvent, or we could have an ionic and a polar. Delta H1, which is the energy it takes to break the solute molecules from each other, is large because they're held together by strong intermolecular forces. Delta H2, that's the energy it takes to break the solvent molecules from each other before they're mixed, excuse me, or part of the mixing. That's large because they have that high intermolecular forces. When you mix them together and the polar solute and the polar solvent makes bonds with each other, that's delta H3, and because they make strong intermolecular forces with each other, delta H3 is large and negative. So the delta H of the solution, if you put all these together, a negative and two positives, ends up being small, and the solution, positive or negative, depending on the size of these, and the solution will form. If you do a nonpolar solute, it does not take much to break them up from each other because their intermolecular forces are small. But the polar solvent needs a lot of energy to break it from, so water molecules separate from another water molecule. Then when you put them together, they're intermolecular forces of each other. So this is sort of like if I was to put oil and water together. Oil is nonpolar. Doesn't take that much to break the molecules from each other. Water is polar. Takes a lot to break one molecule from another one in order to go and dissolve this. What the payback is not enough, because if water tries to surround the oil, that's a very small delta H because their intermolecular force are small. So no solution forms. I'm not going to go through the rest of it. You get the idea. It has to do with the intermolecular forces and the strength of them and whether or not the solution is going to be formed. There are other energy factors involved. One of them is called entropy, and that will be covered in Chem 201. So this is the homework just for these two sections. The homework for the first section was given in the other video, and it's at a different page of the packet. And then we'll have one more video to finish this off.